Okay, welcome back. Here we're covering our fourth lecture, or fourth video on lecture 14. And we're going to be looking at practice problems from part 2 of lecture 14. Okay, so these are all problems about reflection and refraction. Well, most of them. This first one is just about the photon nature of light. So I asked here, one photon of ultraviolet light has the equivalent energy of how many photons of infrared light? Okay, so let's use our formula for the energy of a photon, which we know should just be HF. So that means that for the UV light, right, so that high energy harmful light, it would just be H times, and then we have 10 nanometers. So then we think about it, F is equal to C over lambda, okay, because speed of light is constant, right? And so we didn't mention this as any other material, we can definitely use it or think of it as in a vacuum. So that's our UV. Meanwhile, the energy of the infrared light, so IF for infrared, all right, is then going to be H also, and this here, right, and this will be, I'll make this one 1, and this will just be C times lambda over 2, okay? So now I want to find out, what's the ratio, like how many of the energy of UV are equal to the energy of the infrared. Okay, so then I take the ratio here of UV over infrared. All right, I got 8 Planck's constant, speed of light, and then so you probably see how everything's going to cancel out, at least all the constants will. Okay, and so then we're going to end up with lambda 2 over lambda 1, which will be 940 nanometers divided by 10 nanometers, or 94. So in other words, it takes 94 TV remote control photons to equal 1 UV photon. And those UV photons are the ones that give you sunburns. Okay? So it's 94 times more energy per photon for UV light than infrared light. Okay? And you could compare this to, say, visible red light, and you get a value of about like 63, right? So visible red light is 1/63 as high energy per photon as ultraviolet light. Okay, hopefully it makes sense. All right, let's look at some quick concept questions. So in question 1, as the angle of incidence is increased for a ray incident on a reflecting surface, the angle between the incident and reflected rays ultimately approaches what value? Okay. So the idea is, let's get our surface. So we'll draw our flat surface here. And so the idea is that, and we have our normal direction coming straight up. Okay. This is our normal. So if I have a incident ray that's kind of coming in, right? So if I have it come in at some angle, like so, and then it gets reflected at the exact same angle relative to the normal, then if I was to have that angle become increasingly large, right? So I'm increasing this reflected ray, right? So I'm making it so it's this angle here, theta, this angle here, you can see what I'm referring to. Theta 1 is getting larger and larger. Well, that means that theta 1 prime would also be getting larger and larger. And so ultimately, the angle between this ray and this one, so the angle between the two rays, as asked in the question, would approach 180 degrees. So it approaches 180 degrees. Right, so that would be the case where it just barely is actually reflected. It's almost just parallel, right? And or at least you can imagine a case where it's like 1 degree or something off. In other words, with this angle here is 90 or 89 degrees. And then the reflected ray would also be at 89, and we get a sum of 178. Okay. All right. So question 2: when light travels from air into water, what happens to the following properties of the light? The speed, the wavelength, the frequency, and energy. Okay. So first of all, let's be clear on the refractive index change here. So the idea is that the refractive index of water is greater than the refractive index of air. In fact, like I said, it's 1.33 is greater than 1. So I'll just write that 1.33 is greater than 1, because that's the most common refractive index of water. Depends on the properties of water, right? Salt water versus fresh water and so on. but 1.33 is a common value. And then error is approximately 1. So what does that mean then? Well, that definitely means that the speed should be decreased. Okay, so we're asked what happens. So the speed is decreased because it slows down in the water. That's what the higher refractive index means. The wavelength is decreased as well. Okay, that's how the speed is going down. So wavelength is decreased. All right, and that's just based on the idea that C equals lambda F. And so that brings up the topic of frequency, because frequency doesn't change. Refraction, passing from one medium to another, has no effect on the frequency of the light. And again, that's kind of baked into the very modern physics idea of the atoms absorbing and re-emitting the light, because that frequency, there's nothing in there that's changing the frequency. The rate is the same, but the actual length of the waves, the distance between them, is physically changed. So no change on the frequency. And lastly, the energy. Well, if the frequency isn't changing, then the energy isn't changing either. I'll say of instead of on. So no change of energy either. And in fact, if you think about it, that's almost the best explanation of why the frequency doesn't change, because it's the same light. There has to be conservation of energy. The energy didn't go anywhere because all the atoms in the transparent material, water in this case, are absorbing the photon, causing an electron to get excited. That electron then gets relaxed, re-emitting the photon. I know I keep mentioning that, and it's not material we're going to get into until a later chapter, but certainly you've seen atoms and the idea of electrons in other classes, namely chemistry classes. But here's the thing. That has to be a conservative process. There's no friction inside the atom. That energy is completely conserved. Whatever energy is absorbed by the atoms of the transparent material are emitted by the atoms of the transparent material. And so if the energy isn't changing, then the frequency can't change either, right? Which means that's why the wavelength must, because certainly the speed is slower. Okay. All right, question 3. A laser beam passing from medium 1 to medium 2 is refracted as shown. What must be true about the index of refraction of the two mediums? Okay, so this is one I want you to think about. I gave you the idea about when it bends away from the normal or not. So make sure you understand what that means, and then I think you'll be in good shape to answer this question on your own. Of course, I'll post the solution eventually, but for now, go ahead and put some thought into this one. Okay, so let's do our a first actual computational example with refraction. Okay, so an oil film floats on a water surface. The indices of refraction for water and oil, respectively, are 1.33 and 1.466. 333, that is. If a ray of light is incident on the air to oil surface at an angle of 41.9 degrees with the normal, what is the incident angle at the oil to water interface? So let's draw a picture of this. So this will represent the interface from air to oil, and then that's the whole oil thickness, and then down below is water. Okay, so then I'll label which are which. So this is going to be our N of 1 up here for the air. This will be our N of 1.466 actually, for the oil. And then underneath is the water at 1.333, okay? And so then we have our incident ray coming in. So our ray is going to come in at 41.9 degrees. Okay, and that's relative to the normal, like so. All right, and then that ray will get bent further towards the normal. So actually, let me continue my normal line a little bit longer. So it goes right through. All right, and then actually I want to draw this steeper. It's too hard to see. All right, so there's our normal line. And then we redraw that incident ray. All right, so there we go. So there's the incident ray. It's then going to get bent towards the normal. And then when it passes to this next one, it's then going to get bent away from the normal because it's going from higher to lower. So I'll draw another vertical line for for this normal direction. And attempted a vertical line, there we go. And then I'll have it bend away, like so. Zoom in a tad on that so you can see it more clearly. So maybe something like this, okay? And so then we'll label all of our angles. All right, let's go ahead and do that in pink this time, probably good color for the angles. We've been doing a lot of angles here. So this one will simply be theta 1. This here will be theta 2. This one here is going to be theta 2 as well, as you can see from the geometry. And then this one here will be theta 3. Okay, looks good. All right, so let's think about how we would set that up. So we'd set up Snell's law. Okay, so we're really putting it to practice here. So we'd have our n1 sine theta 1 equals n2 sine theta 2. I'm going to want to solve for theta 2. So then theta 2 is then going to equal n1 over n2 times sine theta 1. But of course, that's going to need to be inside of an inverse sine function. So sine inverse of all that. Okay. And so let's see what we get. So that will be sine inverse. And then we'll have 1 over 2. So it's going to be 1 over 1.466. And then times sine of 41.9 degrees. Okay. So we'll go ahead and calculate that. So sine inverse, 1 divided by 1.466 times sine of 41.9. All right, so I get 27.1. So 27.1 degrees. Okay, and now I want to do something very similar for theta 2. For theta 2, I'll just write up here where it's going to come from. So in this case, it would just be n3, and then let me add some subscripts over here to the figure, so you know which is which. That's n1, that's n2, and this is the n3. Okay, and so we'd have n3 sine of theta 2. So sine of n2 sine of theta 2 equals n3 sine of theta 3. Okay, that's just what's going on, going from theta 2 to theta 3. Okay, or passing from material 2 to the material 3. In other words, passing from the oil into the water. And here we should expect it to bend back, not back to 41.9, but we should expect theta 3 to be bigger because we went down in index of refraction. Whereas here we went up in index of refraction. We went from 1 to the larger value of 1.466. All right, so we'll just find that final value. So when we solve for Snell's law, it will have the same form. So in this case, though, it's just going to be n2 over n3. And then it'll be sine of theta 2 that we found in the first step. So the numbers will just be this. So it's just going to be 1.466 divided by 1.333, and then sine of 27.1 degrees. Okay, so let's see what we get for that. So 1.466 divided by 1.333, and then times sine of 27.1. All right, so 30.1 degrees. All right, so you can see that you can then, really have it pass through as many materials as you want, as long as you just follow each refraction, each bending one interface at a time. First interface was the air to oil, then the second interface was oil to water. All right. Okay, so I'll leave example 3 for further practice. It's a good one for you all to give a try. Let's look at a problem here that has some reflection in it. So this is a good problem involving a little bit of reflection. Basically a geometry problem, like a lot of these are. All right, so let's take a look at that. So, all right, so we have a bulb that's 1 meter away, and then the light is coming down at the very top of the mirror, and then we're asked for how far it gets bounced away from the mirror. Okay, and we can, as it's pointed out here, that the angles are the same by the law of reflection, which will allow us to draw our triangles and find our values. Okay, So ultimately, I want to find theta. So theta is then going to be equal to tangent inverse of 0.5 over 1. All right, so let's go ahead and do that. All right, so that's 26.6 degrees. Okay, and then, so then based on that, we can see then we have a triangle where we want to find L, and we know that this theta must be the same. It must also be 26.6, and likewise, that means that this must be 26.6. So then we can say that we have cosine of theta is going to be L over 2 meters, and that allows us to solve for L. So then L is just going to be 2 meters times cosine of 26.6 degrees. So you can see how the law of reflection allows us to set up these really nice triangles. Okay, so cosine of 26. Okay, so 1.79 meters. Okay, and wait. Oh, I used the wrong function. Yeah, I'm like, that's not right. It can't be shorter. That's because I should have used tangent. Is tangent of theta, because there's no hypotenuse there. And that would be opposite over, okay, yeah. So there should be a tangent right here. Okay, so let's fix that. All right. Tangent. All right, so 2 opposite over adjacent, 26 degrees. Oh, so this is 2 meters over L, which means then we solve for L, we get, it would then be 2 meters divided by tangent. There, finally. All right. So 4 meters, that makes sense. Okay, because we actually could have, instead of even finding an angle, we could have just carried it through by the definition of 0.5. So it'd just be 2 divided by 0.5. All right, so 4 meters is our distance that the light beam gets reflected out across the floor, so the light beam would hit the floor 4 meters away from the edge of the wall. Okay. All right, so we got a concept question here. We can definitely take a look at. So the idea with this concept question is it's a prism. This is kind of what you'll be seeing in the post quiz, in next week's post quiz. And so the important thing about the prism is you have to think more carefully about the normal, because the normal direction, rather than just being straight up or straight down or something, or even horizontal, it has to be normal to the surface, so it's perpendicular. So it just behooves us to kind of like draw it carefully and think about it and do our geometry and so on. So we'll go ahead and draw the normal direction. So I'm just going to have it drawn in the way that it looks perpendicular to the surface. Okay. And so then we have a case here where I want it to be perpendicular. Okay. Something like that. Okay. And I'll copy both of these and let's put them over where we need them. So here we'll have it again. Okay, just gonna move this one down a tad so we can kind of clearly see. So all I'm doing here is just getting our normal vectors so they help us see if the angle is getting bigger or smaller in each case. Okay. Okay, so we're told that it enters the glass, then which is the possible path, okay? So that means that we know when it enters the glass, it has to bend towards the normal because it's going from air to glass. It's going from a higher speed in the air to a lower speed in the glass, from a index of refraction of 1 to an index of refraction greater than 1 in the glass. So which of these cases, A, B, C, or D, do we have the light ray bending towards the normal? Okay, so if we take a look at it, we can see that clearly in B, it bends towards the normal. So in other words, we have a reduction in the angle, right? So like theta 1 is that angle, and we have theta 2 being smaller. All right, are there any others that meet that criteria? Well, no, definitely C doesn't. In this case, looking at theta 1 and theta 2, and for theta 2 is bigger in that case, so that definitely doesn't work. Likewise, if we look at A, theta 1 is smaller than theta 2, so that's bending away from the normal. And then looking over here at D, we have theta 1, okay, and then we got theta 2. So theta 2 also, so D also works. So we've narrowed it down to B and D. Okay, but then we know when the beam leaves the glass, it has to bend away from the normal because now it's returning to air with a higher speed. So, okay, so let's look at B. So in B, is it bending away from the normal? No, it bends further towards the normal, okay? So we have here that if we look at theta 3, we have that theta 3, or actually call it theta 4, so we'll call this one theta 3, because unlike with the flat surfaces, we don't have that direct angle. So in other words, theta 3 at the prism here is not equal to theta 2. It's related to the apex angle, alpha, and you can solve it with geometry, but they're not equal to each other. But regardless, theta 3 and theta 4 are going the wrong way. So theta 4 is smaller than theta 3, and that can't happen. It can't bend towards the normal as it speeds up. It has to bend away from the normal, which you clearly see is satisfied with option D. So option D works, and it works because, and I'll put this in writing. So option D is the correct answer, and it's because theta 2 is smaller than theta 1, and theta 4 is larger than theta 3. And that has to be the case. And that's the only picture shown, the only ray diagram shown that's correct is D. Right? So that's a very good example because there's a lot packed in there. Okay. Now we should do one computational problem that involves something that has the properties of a prism essentially. In the interest of time, I'll just post this solution. I want to wrap this video up, so let me kind of just give a quick synopsis of what's going on. So we got a few further example problems. Example 6 is a good one to try. I'll go ahead and post solutions to example 5 and example 7, and I'm happy to answer any questions about that. But I think my solutions should elaborate on the approach that's taken. And these are similar to some of the problems that are found in the homework. There's a problem similar to example 7, and there's also a problem similar to example 5. Okay, well, thanks for listening to this series of 4 videos for